In this video, I'm going to discuss the normal approximation to the binomial distribution, and I'm also going to discuss the central limit theorem and using the central limit theorem to solve a probability. Okay, so let's go ahead and read through the problem and see what's going on. So we have a six-sided die that's rolled 350 times. Okay, so it's rolled a ton of times. Find the probability that a 5 or a 6 is rolled at least 120 times. All right, so before you came to this chapter where we're using the normal approximation for the binomial distribution, using your tools in your toolbox, you might have said, okay, well, this is a binomial because we have either a success or failure. You roll a 5 or a 6 or you don't. Each trial is independent, right? You're rolling a die, and there's a set number of times that you're rolling it. You're rolling it 350 times, basically counting if you have 120 successes or more, right? So at least 120 successes. So let's define the random variable, x. X will be the number of times that you roll that a 5 or 6 is rolled out of 350 trials or 350 rolls. Okay, so x is binomial. Okay, so notice that x is, I'm going to use the squiggly line to note that it is binomial. Okay, and n for this binomial distribution of x, n would be 350. Okay, and p, the probability of success for this binomial distribution. Okay, so you can roll a 5 or a 6 and it's considered a success. So there are six total sides on the die. So that's 2 out of 6 are a success. 2 out of 6 is the same as 1 out of 3, or 0.3333, right? So this is our random variable x is binomially distributed with n is 350 and p is 1/3. Okay, so now if we're trying to find the probability for part A that x is at least, so greater than or equal to 120. Okay, so I have 120 successes or more. Now, before we had the normal approximation, we could have solved this using the probability mass function for the binomial, right? Remember, for binomial, it's n, choose x, p to the x, q to the n minus x, right? So we would need to sum that up. We need to sum it up from x equals 120 until x equals 350. And so n is 350, choose x, right? You'd plug this in as you sum. P is 1/3 to the x, and q is 2/3, because 1 minus 1/3 is 2/3, and this would be to the 350 minus x. Okay, so if you have a computer or your calculator, you can do this sum. Now, you're not going to sit there and do this sum by hand, because that would take a really long time, right? You have to sum from 120 all the way to 350. Okay, so statisticians a long time ago, since they didn't have access to computers and such, they realized that binomial distribution, as long as n times p and n times p times q are so in other words, as long as the mean and the standard deviation are more than 5, then the binomial distribution is actually really close to being a normal distribution. So we could solve this by using a normal distribution a lot faster than we could sit down and do all the sums. Okay? So let's see. If we were to use the normal distribution, so let's draw this out. Actually, let me not draw the shape of the distribution yet. So in the center of this distribution, the center of the distribution for x should be its mean, right? So let me go ahead and calculate the mean of this distribution. So the mean, or the expected value, remember, expected value is the same thing as mu, right? For a binomial distribution, it would be n times p. N times p would be 350 times 1/3, which in this case, this comes to about 116.67. Okay, so 116.67. Okay, so what does this mean, this average, right? This means that if you were to roll the die 350 times, and you say you were to roll the die 350 times over and over and over again, on average, you get 116.67 on average. This is the number of successes that you would have, or the number of times that you would have successfully rolled a 5 or a 6. Okay, so we would successfully roll a 5 or a 6 about 116 times, or 117 times. All right, then from there, so that would be the most likely outcome, right? So that's the highest probability. Then from there, it's less and less likely that you'll roll, so it's less likely that you'd roll like 130 5 or 6s, right? If you rolled the die 350 times. It's less likely that you'd roll 100 5 or 6s if you rolled the die 350 times. So this is symmetric around the center, okay? So it's roughly like a normal distribution, right? So this is x down here. So these are all the x values, and this is kind of like the probability, and it's symmetric around the mean, right? And that's why it looks like a normal distribution, okay? And it is approximately normal, okay? And that's what we're going to be using to solve this. So this is approximately normal. All right, so let's see. So if we say this is approximately normal, this is the distribution of x, which is binomial, then how are we going to solve this? Okay, so let's see. We have the probability that x is greater than or equal to 120. Let's see, where is 120? 120 would be somewhere around up here. 120. Now, this is not, because x is discrete, right? This is not continuous, all right? So this is actually, instead of it being it's actually kind of like a block, right? All right, all of these are just little blocks, because remember, x is discrete. So these are like little blocks, right? They're like little blocks like this. When we use the normal approximation, to the binomial distribution, we're smoothing over all these little blocks, right? So in the center of each block would be, so this would be 120, this would be 119, this would be 118, this would be 117, the center of each block, right? And this would be actually, was I going in the wrong direction? Yes, I was. This would be 121, 122, 123. Yeah, of course, that's going upwards, right? So this would be 121, 122, upwards. And then this would be 119 down here, okay, in the center of the block that's right after this block. Okay? All right, so we want to find the probability that x is greater than 120. So greater than 120 would be over in this direction. Now notice I only am going up to this line here, the 120 line, but I want to fill in all these blocks that are greater than. All right. Now I want greater than or equal to 120, so I should go all the way over on this block to halfway between 120 and 119. All right, that going halfway over, that's called the continuity correction, okay? So going from 120 to 119 to like fill in this block here, that's the continuity correction. All right, so let me go ahead and write this down. So what I'm saying is that this is going to equal the probability that x is greater than 119.5, right? That's halfway between 119 and 120. Okay, and this is the continuity correction. Okay, and this is the normal approximation to the binomial. So over here, x is binomial. Over here, x is normal. Okay, and that's very important, right? All right. So once we've made that switch from the binomial to the normal distribution, now we just treat this like a normal distribution. All right. So we'll need to take this and make it into a z value. So remember z. Oops. Let me switch that around. Greater than. So z would be. Let me go ahead and write this down here. Z is equal to x minus mu divided by sigma. So what's sigma here? I need to calculate it, right? So I found mu, n times p. Remember, sigma would be the square root of n times p times q for the binomial distribution. So this would be the square root of 350 times 1/3 times 2/3. Okay, and so that comes to, I think, square root of 77.78, something like that. So let me go ahead and write that here. So the x is 119.5 minus mu, which is 116.67 divided by the square root of 77.78. Okay, and that comes to about, let's see, 0.32. All right, so if I want to then calculate, if I want to go back, so this is the same, this probability of x, the same thing as the probability that z is greater than 0.32. And if you want to use your table, you have to flip that around. 1 minus the probability that z is less than 0.32. And you look up 0.32 in your table, and you get 0.6255. So 1 minus that is 0.3745. Okay? And that would be your answer. So the probability that you roll a 5 or a 6 at least 120 times is 0.3745. All right, so now let's switch this up. So that one was at least 120 times. Now let's say less than 100 times. Okay, and by switching around the sign of the inequality, that is going to change the way we do the continuity correction. So let's talk about how that changes things. All right, so I'm going to scroll over to do this one. Okay, so for part B, probability x is less than 100. Okay? All right, so now if I were in the world where I'm using, the binomial distribution, right, you could always do the sum x equals, you wouldn't start at 100, right? You actually, let's see, since less than 100, you'd start at 0. And you wouldn't go all the way to 100 because it's not less than or equal to 100, it's less than. So you go to 99, right? And then you could do this sum. So 350, choose x, 1/3 to the power of x, and 2/3 to the power of 350 minus x. Okay? So if you were to solve it using the binomial distribution, this is the way you would solve it. But because that takes a long time to compute, we have the normal approximation. So let's talk about how to use the normal approximation, okay? So over here, x is binomial, less than 100. Now, less than 100, we just talked about. This is the same thing as x being less than or equal to 99, okay? So whenever you're using the normal approximation to the binomial, it's helpful to bring it to something that's like includes the equal sign, okay? That helps. So then do that first. So here, x is binomial, right? X is still binomial. Okay, let's draw out our curve. Actually, okay. So here is 116.67, all right? I'm going to put 99 down here. All right, and it has a block around it because it's continuous. This is the continuous curve for a discrete distribution. Okay, so these are the x values. Okay, so over here would be 100. Over here, right, would be 98. All right, so I can draw those two little blocks too. All right, 100. All right. Okay. So we want the probability that x is less than or equal to 99. So let me draw that. Here's 99. Here's our equal to 99 and less than. All right. So all this down here. Now, since it's less than or equal to, I want to include this entire block, right? So I'm going to need to go to halfway between 99 and 100. So I'll need to go to 99.5, right? Because that's halfway between 99 and 100. So I'll do, this is the same thing as the probability that x is less than 99.5, right? That's basically me filling in this entire block. Okay, so then it's all this over here. All right, so notice in this problem, we added half, basically, right? Because we wanted to go between 99 and 100. And this was a probability for less than. However, in this problem, recall, since we had 120 and we wanted to do more than 120, we actually had to go back, right? Because what you're trying to do is you're trying to fill in the entire block for the equal sign, right? So in this problem, you went back half. But in this problem, because you went to 119.5, but in this problem, you go forward half, right? So it's really helpful to draw these out and then determine, you know, if you need to go up a little bit or back a little bit as part of your continuity correction. All right. All right, then from here, you can go ahead and solve this. You have the same standard deviation and mean. I went ahead and did this. You can double check. So this is z less than negative 1.833. Negative 1.83. So you can go ahead and see if you calculate that the same way. Actually, sorry, 1.95. Negative 1.95. Okay, so go ahead and calculate the z and see if you get the same. You should. It's using the same standard deviation and same mean. Okay, and then if you go to your table, you should see that this probability is 0.0256. Okay, so now let's go on to part C, where we have now the experiment is being repeated. Okay, so we have repeating the experiment 25 times. So that means we're rolling the die 350 times, and then we're rolling the die again 350 times, again 350 times. We're rolling the die 350 times, total of 25 times. Okay, and now we're finding the probability that the average. Okay, so once we've rolled the die 25 times, we're going to have an average, right? So like say on the first time we rolled the die, there was exactly 100 5 or 6s, right? Second time we roll the die, there might be exactly 120 5 or 6s. The third time we roll the die, there might be exactly 118 5 or 6s, right? So we're going to roll it 25 total times, and then we're going to see the average number of successful rolls out of the 350 rolls. We want to know whether or not what's the probability that that average is at most 115. So we want to find the probability of the average. Remember, average would then be x bar, right? So x bar is the average of x, right? The sample average of x, right? So let me write sample average of x, where the number of rolls here, or the number of samples, is 25, right? Okay, so sample average, the sample average of 25 different experiments. So So now we want to find the probability that this sample average is at most 115. So at most, remember, means less than or equal to, right? So let me go ahead and move down, and we'll talk about how to solve this one. So for part C, trying to figure out the probability that x bar is less than or equal to 115. All right. So now, x bar is not binomially distributed, right? X bar is the sample average, okay, of 25 samples, right? X bar is not binomially distributed. Recall x is binomially distributed, but x bar, the sample mean of those x's, is not. Okay, so we're not going to be using the normal approximation to binomial in this to solve this. Rather, we're going to use the central limit theorem. Now, the central limit theorem says that x bar is approximately normal as long as the sample size is large enough, right? And sample size of 25 here is going to be large enough for this, the distribution of this mean to be approximately normal, okay? So it is going to be approximately normal. Now, the mean of x bar is the same as the mean of x, right, by the central limit theorem. So this is by CLT, okay? So both these things are by CLT. Okay, so the mean of x, the mean of the binomial distribution, we found it out already to be 116.67, okay? And the standard deviation of the mean is sigma over the square root of n by the central limit theorem. Remember, sigma for x was the square root of 77.78, okay? And n here is not referring to the n for the binomial, it's referring to the sample size, right, for your x bar. So this would be 25. Right, so in other words, we can put this all under one square root. All right, so this is the standard deviation for x bar. All right, so now if I want to calculate this probability, I'm not using continuity correction, I'm not using anything. All I'm using is the central limit theorem. So it's, x is continuous to begin with, right? Because it's an average, and an average can be a non-integer, right? So it does not have to be 120 or 119 successes, right? If you average over 25 different trials, your average could be 119.5, right? Because it's an average of 25 different trials. Okay. All right. So now, no need for continuity correction. All right. So I don't care about the equality, whether or not it's there, because x bar is already continuous. Remember, for continuous random variables, whether or not you have the equality, it's kind of meaningless, right? Because the probability x bar equals 115 is 0 as long as x bar is continuous, okay? So now if I want to calculate z, I would do 115 minus the mean of x bar, 116.67, and divide that by the standard deviation of x bar, okay? And if you calculate this, I think you should get negative 0.95. Okay, so this is the probability that z is less than negative 0.95, which is 0.1711.